Alright, let's go. Number 10. The quantum Darwinism information paradox. Wojciech Zurek wasn't trying to solve the biggest problem in physics. He was trying to explain something almost embarrassingly basic: why the world looks classical at all. Why a table feels solid instead of smeared across a haze of probabilities. Standard quantum theory says systems exist in superposition until measured. Fine at the particle level. But nothing about the math explains why you and I never see a chair in two places at once. Something has to bridge the gap between the quantum substrate and the solid, boring world we live in. Zurek's answer, developed through the 2000s and confirmed experimentally in photon environment systems, was elegant. The environment, air molecules, photons, anything bouncing off an object, copies the object's quantum state redundantly, over and over, into countless independent witnesses. You perceive solidity because your eyes are reading one of billions of identical copies. This is quantum Darwinism. But here's the stumble. If every interaction imprints a new redundant copy into the environment, the total information content of the universe should be climbing constantly. Unitarity, the rule that total quantum information is conserved, never created, never destroyed, does not obviously permit that. Zurek's papers never resolved where the apparent information amplification goes. Physicists have proposed that the copies aren't truly independent, that some deep entanglement structure keeps the books balanced. No experiment has confirmed it. The mechanism that explains why reality looks solid to you is quietly incompatible, or at minimum unresolved, with the law that says information can't multiply. Every second, your body is being copied, redundantly, quantum mechanically, into the room around you. Nobody knows where that information goes when you leave it. The framework that explains why the world looks real doesn't explain how reality stays honest. 9 down. And the next one is worse. What if a particle's answer depends entirely on what you happen to ask alongside it? Number 9. Quantum contextuality. In 1967, Simon Cochin and Ernst Specker weren't trying to unsettle anyone. They were checking a mathematical loose end, whether quantum particles could be assigned fixed, definite values ahead of measurement, the way a coffee mug has a definite temperature regardless of what else is happening in the room. Classical physics assumes yes. An object's properties exist independently of what you choose to measure alongside them. Measure temperature, measure pressure, measure both. The readings shouldn't interfere with each other if the instruments are compatible. Cochin and Specker proved it's impossible. Quantum mechanics is irreducibly contextual. There is no way to assign fixed values to all observables independent of context. The Cochin-Specker theorem has been experimentally confirmed across multiple physical systems since the 1990s. Ask a particle for its spin while measuring one set of compatible observables, and you get one answer. Ask the identical question while measuring a different, equally compatible set, and the answer changes. Same particle. Same spin. Different answer, depending only on what else was asked. Physicists tried to preserve classical intuition with hidden variable models, the idea that particles secretly carry fixed values we just can't access. Cochin-Specker rules this out for any non-contextual version. Every attempt to rescue a mug-like particle, one with fixed properties regardless of context, fails mathematically. The universe does not give you an answer. It gives you an answer relative to the question you asked alongside it. Your own body is built from particles that don't have fixed properties waiting to be discovered, only properties conditioned on context. What does that mean for anything you think you know about your own physical state, right now, unmeasured? Nobody has an answer, because the question itself may not be well formed. That contextual instability is unsettling on its own. It gets worse when you realize physicists can't even agree on what a measurement is. Number 8. The measurement problem's 3 unsolvable horns. David Wallace and Christopher Timpson weren't trying to create a crisis in 2019. They were trying to organize one that had existed, unresolved, for 90 years. Cataloging every serious interpretation of quantum mechanics into a clean taxonomy. The standard picture says a quantum system evolves smoothly according to the Schrödinger equation until it's measured, at which point it collapses into one definite outcome. That collapse is doing enormous philosophical work, and nobody agrees on what it actually is. Wallace and Timpson's taxonomy reduces every interpretation to three horns. The wave function is complete and real and never collapses. Many worlds. The wave function is complete and sometimes really does collapse, but then you need a physical mechanism nobody has found, one that likely conflicts with special relativity. Or the wave function is incomplete, and hidden variables exist, but Bell's theorem forces those hidden variables to be non-local. Every interpretation of quantum mechanics falls into one of these three camps. None is experimentally distinguishable from the others. A 2019 survey at a Quantum Foundations conference found no dominant interpretation, 90 years after the theory was formalized. Physicists have tried majority votes, elegance arguments, philosophical intuition. None of it counts as evidence. The three horns remain equally viable and equally untestable. The device in your pocket runs on quantum mechanics flawlessly. Every transistor, every laser, every chip, built without anyone agreeing on what's actually happening at the moment of measurement. The most successful theory in the history of science works perfectly, and nobody can tell you what it means when it works. 8 down. If measurement itself is unresolved, what happens when entanglement stops respecting the order events happen in? Number 7. Entanglement across time. Eli Megadish and Haggai Eisenberg at Hebrew University weren't trying to break causality. They were testing the limits of entanglement swapping, a well-established technique for linking particles that never directly interacted. Standard entanglement connects particles across space, measure one, and you instantly know something about its partner, however far away. Textbook quantum mechanics. Nothing here should touch time itself. Then the 2013 experiment ran its full sequence. Photon 2 was measured and destroyed before photon 3 even existed. Photons 2 and 3 were then entangled through a Bell state measurement. Except photon 2 no longer existed to be measured directly. The correlations still showed up in photons 1 and 4. Megadish, Eisenberg, and colleagues published the result. Photons 1 and 4, which never coexisted in time, displayed quantum correlations as strong as ordinary entangled pairs. Photon 1 was gone before photon 4 was created. They shared no window of mutual existence. They were still correlated. Physicists proposed this was merely a mathematical bookkeeping trick, not real temporal entanglement, that the correlations were inherited through the measurement chain rather than a literal connection across time. But the correlations are physically real and reproducible regardless of how you narrate them. No explanation removes the fact that particles separated by non-existence, not just distance, remain linked. If quantum correlations don't require two things to coexist, what does that say about the version of you that existed a decade ago, and the version that hasn't happened yet? Entanglement across time doesn't explain the past or the future. It just proves they're not as separate as the clock on your wall insists. 7 down. If time isn't a clean barrier, maybe randomness isn't as blind as thermodynamics assumes. Number 6. Quantum Brownian motion that remembers. Researchers at the University of Vienna and the Austrian Academy of Sciences weren't trying to challenge thermodynamics. They were studying decoherence, how quantum systems lose their quantumness when exposed to a noisy environment. Classical Brownian motion is the textbook picture of pure randomness. A particle jostled by thermal collisions diffuses outward unpredictably, each kick independent of the last, with zero memory. It's the foundation of statistical irreversibility, why heat flows one direction, why entropy climbs. In 2021, the Vienna team found something classical thermodynamics doesn't allow. In a regime where quantum coherence persisted despite thermal noise, the diffusion process retained memory effects, correlations that permitted partial reversal. Their published results showed quantum Brownian motion behaving differently from its classical counterpart, specifically at the boundary where coherence survives thermal jostling. Classical Brownian motion is memoryless by definition. This version wasn't. The obvious explanation that this is just classical randomness dressed up in quantum language doesn't survive scrutiny, because the reversal effect depends explicitly on coherence that has no classical counterpart. Alternative explanations invoking measurement artifacts have not accounted for the reproducibility of the memory signature across trials. Every irreversible process in your life, your cells aging, heat leaving your coffee, the entropy of your own body climbing toward disorder, rests on the assumption that thermal randomness has no memory. At the quantum level, that assumption breaks. Nobody has explained where classical irreversibility actually comes from if its quantum foundation isn't blind after all. 6 down. And measurement itself can produce answers no particle should be able to give. Number 5. Weak values that are physically impossible. Yakir Aharonov, David Albert, and Lev Vaidman weren't trying to break measurement theory in 1988. They were formalizing a mathematical technique, weak measurement, gentle enough not to fully collapse a wave function, combined with post-selecting only specific final outcomes. Standard quantum measurement gives you one of a fixed set of allowed outcomes. A spin 1/2 particle can only ever read out as +1/2 or -1/2. That's the rule. No exceptions. In any strong measurement ever, weak measurement broke the rule's spirit while staying mathematically rigorous. A spin 1/2 particle, measured weakly and post-selected on a specific later outcome, can yield a weak value of 100. A particle's kinetic energy, measured weakly, can come back negative, for a quantity that is always positive in every strong measurement ever performed. These aren't errors. Aharonov, Albert, and Vaidman's framework predicted them, and experiments have reproduced them since. The results are treated as legitimate information about the quantum system's state between two measurements, the past state conditioned on a specific future outcome. What that actually means physically remains contested. Some physicists argue weak values describe nothing real at all, merely statistical artifacts of averaging, but the reproducibility across independent labs undercuts a purely artifactual reading. A measurement gave an answer that is, by definition, impossible for any single particle to have. It was reproducible. It was consistent with the theory. Both of those things are true at once. If asking gently gets you an answer that asking firmly rules out entirely, what does that say about what's true of a particle when nobody's watching? 5 down. Even the rule that governs every quantum probability might not be as fundamental as it looks. Number 4. When the Born rule stops applying. Anthony Valentini at Clemson University wasn't trying to overthrow quantum probability. He was working through the implications of pilot wave theory, the de Broglie-Bohm framework, where particles have definite trajectories guided by a wave. The Born rule is the most precisely tested law in physics, the rule that the probability of an outcome equals the square of the wave function's amplitude. It's confirmed to extraordinary precision, in every experiment, every time. Valentini's framework treats the Born rule not as fundamental, but as an equilibrium condition, analogous to thermal equilibrium in statistical mechanics, which means, in principle, quantum systems could exist out of that equilibrium, out of Born rule behavior entirely. Valentini calculated that particles produced in the earliest moments of the universe, before quantum equilibrium was established, could retain statistical signatures of non-equilibrium behavior, potentially detectable today in relic radiation like the cosmic microwave background. No confirmed violation has ever been observed. Critics argue the equilibration process would have erased any such signature long before the CMB formed, leaving nothing to find. Valentini's response is that equilibration timescales are model-dependent and haven't been ruled out. Neither side has closed the argument. The rule that governs literally every probability in quantum mechanics, the rule your phone's random number generator ultimately depends on, might be a local equilibrium, not a law. We've been staring at the cosmic microwave background for decades. We have not confirmed a violation. We have not ruled one out either. 4 down. Some symmetries in nature are broken exactly where physics predicts. This one is broken in the opposite direction, too clean, with no explanation why. Number 3. The strong CP problem. Nobody set out looking for missing symmetry violation. Physicists working out the consequences of quantum chromodynamics in the 1970s were simply following the math of the strong force. The force binding quarks inside every proton and neutron in your body. The QCD Lagrangian naturally contains a term, the theta term, that should produce CP violation, a measurable asymmetry between matter and antimatter behavior inside the strong force. The theory demands it exist at some detectable level. Experiments measuring the neutron's electric dipole moment, which strong CP violation would generate, have found nothing. The current upper bound on the theta parameter sits below 1 times 10 to the power of minus 10. Effectively zero. There is no theoretical reason for theta to land that close to zero. Roberto Pecce and Helen Quinn proposed a new symmetry in the 1970s whose spontaneous breaking would dynamically drive theta towards zero, predicting a new particle in the process, the axion. Decades of searches by ADMX, Haystack, and Abracadabra have found no trace of it. Physicists have also tried anthropic arguments that only universes with near zero theta permit stable matter, so of course we'd observe this value. It doesn't explain the mechanism, only why we'd be here to see it, which isn't the same as solving the problem. The strong force is more symmetric than the equations governing it require. Every quark inside every atom in your bones obeys a symmetry with no confirmed origin. 50 years. Still unresolved, still missing its explanatory particle. 3 down. If forces are more orderly than they should be, maybe space-time itself is smoother than quantum gravity demands. Number 2. The missing quantum foam. John Wheeler wasn't trying to make a falsifiable prediction people would spend 60 years chasing. In 1955, he was simply asking what happens when you apply quantum uncertainty to the geometry of space-time itself, at the smallest conceivable scale. Quantum gravity, taken seriously, predicts space-time becomes a turbulent structure at the Planck length, 10 to the power of minus 35 meters. A churning foam of virtual black holes and wormholes flickering in and out of existence. This isn't speculation. It's a direct consequence of combining quantum mechanics with general relativity. We built instruments sensitive enough to look. In 2015, Fermi Gamma-Ray Space Telescope observations of gamma-ray bursts from sources billions of light-years away showed photons of vastly different energies arriving simultaneously, constraining foam models to scales far below the Planck length itself. Fermilab's holometer experiment, running from 2012 to 2016, searched directly for holographic noise, the predicted signature of Planck scale graininess. It found nothing at the sensitivity tested. Physicists have argued the foam might exist, but be more subtle than these experiments could catch, a fair point, but one that shrinks the prediction until it barely resembles Wheeler's original picture. Others argue space-time might genuinely be smoother than quantum gravity requires, which would mean something is wrong with how gravity and quantum mechanics are being combined. One of the two, either the sensitivity of our best instruments has failed us, or a direct prediction of quantum gravity, made 70 years ago, is simply incorrect. Space-time itself, the stage everything else happens on, is not confirmed to be granular where the math says it must be. 2 down. Last one saves the strangest data for the body doing the thinking. Number 1. Quantum coherence in neural microtubules. Roger Penrose wasn't trying to explain consciousness when he started. He was working on the mathematics of quantum gravity and objective wave function collapse. Stuart Hameroff, an anesthesiologist, was trying to understand why anesthetic gases switch off awareness without switching off the brain's electrical activity. Together, in 1989 and 1994, they proposed orchestrated objective reduction, the hypothesis that quantum coherence inside microtubules, protein scaffolding within neurons, plays a causal role in consciousness through a gravitationally triggered collapse mechanism. Physicists and neuroscientists dismissed it for 30 years. The standard argument: quantum coherence cannot survive in a warm, wet, noisy biological brain. Decoherence should happen in femtoseconds, far too fast to matter for thought. Then, in 2022, a team led by Jack Tazinski at the University of Alberta published quantum spectroscopy results showing resonance signatures in microtubules at biological temperature. Signatures consistent with coherence surviving longer than standard decoherence models predict. Separately, 2023 research in Physical Review E showed anesthetic gases binding to hydrophobic pockets inside microtubules at sites ORCH or had specifically predicted, with binding strength correlating to anesthetic potency. Skeptics point out that resonance signatures aren't proof of functional coherence relevant to cognition, and binding site correlation isn't causation. Both objections are fair. Neither one explains the data away. 30 years of dismissal. Then 2 independent experimental results landing exactly where a rejected hypothesis said they would. The idea that your consciousness right now involves quantum processes inside your own neurons has 2 data points in its favor and 0 confirmed refutations. That is not the same as being right. It is also not the same as being wrong. 10 anomalies. 10 separate fields: information theory, measurement, time, thermodynamics, cosmology, particle physics, space-time, consciousness. Different papers, different decades, different institutions, and every one of them sits not at some fringe of speculative physics, but at the dead center of our most rigorously tested theories. That's the part worth sitting with. This isn't a list of things physics hasn't gotten to yet. It's a list of places where our best confirmed frameworks quietly stop making sense on their own terms. The universe isn't confused. It's running exactly according to its own rules. We're the ones still arguing about what those rules mean. If you want to see more videos like this, click the video on screen now.